Thanks for the introduction, and thanks everyone for staying for the last talk of the conference. So I'm going to present some PASTA. It is short for password-based threshold authentication. It's joint work with Shashank Agrawal, Pema Mahaso, and Partey Mukherjee at Visa Research. So the first question you want to ask, what problem is PASTA trying to solve? Let's start with the example. When you try to sign in to Dropbox, there is an option of signing in with Google. So how does that work? The open standard of this mechanism is called OAuth, and it works as follows. In this picture, there are three parties: a Google server holding a secret key, a Dropbox server, and a user. The user can use its username and password to somehow request for a token from Google. And then the Google server will verify if the password is correct or not. If it's correct, it will use a secret key to generate a token, which could be a digital signature in this case. And then the user can just forward this token to Dropbox. And then Dropbox server can verify if this is a valid token generated by Google for this particular user. If everything looks good, it will give access to the user. But now, if the Google server is somehow compromised, then there are two issues. First, the secret key is leaked, so the attacker can generate any token to access any Dropbox account. And second, the user's password could also be somehow leaked. I will elaborate more on that later, but let's look at a second example called JSON Web Token, which is a particular type of token that's being widely used in webs and mobile apps. So here's my Gmail app on my cell phone, and whenever I want to access my Gmail account, I don't have to type in my password every time. Instead, I just type in once at the beginning, and then later, I'm just automatically logged in. So how does that work? It's very similar as before, the three parties: a Google server holding a secret key, a Gmail server, and my cell phone. When I type in my password, I'm actually using my username and password to somehow request for a token from Google. And again, the Google server will verify if the password is correct or not. If it's correct, it will use a secret key to generate a token. It could be a digital signature or a MAC in this case. And then I can just store this token locally on my cell phone for later use. And later, whenever I want to access Gmail, I can just send this token to Gmail. And Gmail will verify if this is a valid token generated by Google for me, and so on. If everything looks good, it will give me access. The same issue as before, if the server is somehow compromised, then there are two issues. First, the secret key is leaked, so the attacker can generate any token to get access to any Gmail account. And second, the user's password could also be leaked. And more generally, this issue arises in a lot of password-based token generation protocol where there is a server holding a secret key, there's a user using the username and password to request for a token. The server verifies the password is correct and then issues a token. In this scenario, if the server is corrupted or compromised, then two issues again. First, the secret key is leaked, so the attacker can generate any token. And second, the user's password could also be leaked. Now, let me explain how this is leaked. I guess maybe you have seen this issue many times in this conference, but let me say this again. Normally, in a password-based authentication protocol, it works as follows. So when the user signs up, the server will store the username along with a hash of its password for every user. And then when the user is requesting for a token, it will send its username and hash of its password to the server. And then the server will verify if these two hash values are the same. If they're the same, then the password is correct. It will issue the token. So now the server is compromised. The password is not immediately leaked. But what the adversary can do is that he can try different possible passwords to see if any of these hash values match the hash value stored locally. And this is what we call offline dictionary attack. I'm kind of simplifying the scenario here because I'm not talking about any sorting mechanism. But even if you use a sort, it doesn't trivially solve the problem because the adversary can still try different possible passwords for the public sort. And So this is a high-level idea, and because in reality, the user's passwords are usually chosen from a relatively small space, such kind of attack could succeed with very high possibility. So this is the issue, and our goal of this work at the very high level is the following. Instead of having a single server holding the secret key, we want to have a bunch of servers, and we want to somehow secret share the key among them, such that even if a subset of the servers are corrupted, let's say up to t-1 servers are corrupted, t is the threshold, we still have the following two guarantees. First, the secret key is secure. They cannot recover the secret key. And second, the user's passwords are secure against offline dictionary attack. So this is our goal, and our contribution is the following. We first formalize a new primitive called password-based threshold authentication, or PBTA for short. We motivate the problem and formalize security definition. And then we give a construction of PBTA called PASTA, which is a framework of construction that works for various types of tokens listed here. And finally, we implemented PASTA and gave experimental results. Next, I will briefly look into the definition of PBTA. I won't give you the formal definition, but I want to give you a better sense how it is defined. So PBTA protocol consists of several phases. First, there is a global setup phase, a bunch of servers, and a secret key is shared among them. We have the guarantee that any T servers can jointly recover the secret key. On the other hand, if up to t-1 servers are corrupted, they cannot recover the secret key. So this is a global setup. It's done only once at the beginning of the system. And then after that, every user has a sign-up phase. In the sign-up phase, the user will use a username and password to sign up at every server. Okay. This is done once for every user. But notice here that we don't want the servers to communicate at all. There's only communication between a client to every server. And then after the sign-up phase, a user can again use a username and password to request for a token. And this is a two-round protocol, one round from the client to every server, and then one round from every server back to the client. In the second round, again, there is no communication between the servers. In the second round, every server will use the secret key share to generate kind of a partial token. And then if you have T-valid partial tokens, you will be able to recover a real token. On the other hand, if up to t-1 servers are corrupted, they cannot recover the password by offline dictionary attack or forge a token or guess the secret key. So this is the definition of PBTA. And that's exactly what PASTA is trying to solve. In the rest of the talk, I will tell you how PASTA works and how practical it is. First, how does PASTA work? At a very high level, our construction is a generic construction combining two primitives. The first primitive is called non-interactive threshold token generation, or NITTG for short. You will see in a minute what that means, but essentially, you can think of it as a non-interactive threshold MAC or threshold signature. And we know NITTG schemes for these types of tokens listed here in the literature. The second primitive that we will use is called the threshold oblivious pseudo-random function, or TOPRF for short. It was introduced by Jiraki et al. Last year. We formalized a different definition of TOPRF for our needs, and we prove their protocol is also secure under our definition. And then we combine these two primitives to get a generic construction of PASTA that works for all these types of tokens listed here. And next, I will tell you what are these primitives and how to combine them. First, non-interactive threshold token generation. In this scheme, there are a bunch of parties and a secret key is shared among them. And then, to generate a token, every party will use their secret key share to generate a partial token. And then, if you have T-valid partial tokens, you can recover a real token. On the other hand, if up to T-1 parties are corrupted, they cannot recover the secret key or forge a token. So this is NITTG. And with this scheme, we can actually come up with a naive solution. Okay. As you can imagine, in the naive solution, the secret key share for every party is just the secret key share for the NITTG scheme. And then when the user signs up, every server will store the username along with a hash of its password. And then in the token request phase, the user will send its username and hash of its password to every server. And every server will verify if the hash value is correct. If it's correct, then the password is correct. So it will use the secret key share to generate a partial token. And then if you have enough partial tokens, you can recover a token. In this naive solution, the secret key is secure. If you have up to T-1 servers corrupted, they cannot recover the secret key. However, the password is still not secure against an offline attack. In fact, even if one server is corrupted, the adversary can already run the offline attack to try different possible passwords to match the hash value. So this doesn't work, and that's why we need a second primitive called threshold oblivious pseudo-random function. So TOPRF is a protocol between one client and a bunch of servers. And there is a PRF key shared among the servers. On the client side, the client can take any input X. And this protocol is a two-round protocol. One round from the client to every server, one round from every server back to the client. And the guarantee is that if you have T-valid responses, then the client can recover the PRF value Y. But if you have up to T-1 servers corrupted, they cannot recover the PRF key or reproduce the PRF value Y. Okay, now we have these two primitives. We're ready to construct pasta. First, in the global setup phase, a secret key is shared among the servers. Now we will share two secret keys, one key for NITTG and one key for TOPRF. And then when the user signs up, it will use the username and password as input to the TOPRF protocol. At the end of the protocol, it will learn the PRF output Y. And then using this PRF value Y, it will derive a bunch of secret keys and send them back to the servers. K1 to the first server, K2 to the second server, and so on. Okay. At the end of the sign-up phase, every server will store the username along with the corresponding secret key. Okay. And then after that, in the token request phase, the user will again use its username and password as the input to the TOPRF protocol. At the end of the protocol, it will again learn the PRF value Y and derive the same set of secret keys. In addition, in the second round, every server will use their secret key share of the NITTG scheme to generate a partial token encrypted under the corresponding secret key. So if you have T-valid responses, then the client can use the derived secret keys to decrypt these ciphertexts and get the partial tokens, and then finally recover a real token. And we prove that if you have T-1 servers compromised and even colluding, they cannot recover the secret key or forge a token or guess the password by offline attack. So that's the construction of pasta. And finally, how practical is it? In our implementation, we implemented NITTG for these types of tokens. And as far as we know, the RSA-based digital signature and pairing-based digital signature have not been implemented before. And we also implemented TOPRF, and then we combine these two to get pasta. And here is the experimental results. So in this table, every row is a different type of token, and every column is a different setting. I will explain in a second what plain setting means, but the rest of the settings, every column means a particular number of servers and a particular number of threshold. For example, this column means the number of servers is 6 and the threshold is 3. And the numbers in this table is the time it takes for a client to request for a token. we only consider token request performance because that's used more often, but the sign-up phase is also fast. And this is tested on a LAN network. So now, what is a plan setting? The plan setting is the setting that we discussed at the very beginning of this talk. There's only a single server holding the secret key. And in this setting, if the server is corrupted, then both the secret key and the password could be leaked. So the question is, compared to the plan setting, what is the extra cost of protecting the secret key and the password? And here's the result. If you look at this table, one observation is that if you look at the yellow columns with threshold 2, the numbers are roughly the same. And if you look at the red columns with threshold 3, the numbers are also roughly the same. So we concluded that only the threshold number matters. The total number of servers doesn't affect the performance. And then comparing our PASTA protocol with the plan setting, you can see there is a reasonable constant multiplicative overhead in terms of the performance. And the overhead is slightly higher in the symmetric key-based MAC case. And the reason is that in the plan setting, it is purely symmetric key. But our PASTA protocol inherently uses public key operations. So that's why there's a higher gap there. But we also prove that public key operations are necessary to achieve our goal. So this kind of gap is unavoidable in this case. And then we also tested on a WAN network with 80 milliseconds network latency. And the same observation as before, only threshold matters. And if you compare the LAN setting with the WAN setting, it is roughly plus 80 millisecond round-trip latency, which means the communication rounds is actually a bottleneck, especially in the WAN setting. But I want to emphasize that the round complexity of PASTA is also optimal, just one round from client to server and one round back. So this is kind of the best we can achieve. We have more comprehensive experiments in our paper. For example, what is the time it takes on the client side, how much time it takes on the server side, and how does it compare to the naive solution, namely what is the extra cost of protecting the password, and so on. If you're interested, you can look at our paper. With that, I would like to summarize. Here are the 3 questions that I have been asking during this talk. What is PASTA trying to solve? It is trying to solve password-based threshold authentication, which protects both the secret key and the user's passwords. And how does it work? It is a generic construction combining 2 primitives, and it is a general framework that works for various types of tokens. And is it practical? I would say yes. And hope you like this dish.
Any questions?
Yeah.
Quick basic question. So, do you have any assumptions on how you would protect the set of keys that you derive in the first phase?
Yeah, we rely on the random oracle model. Is that what you're asking?
Oh, okay. So you derive them using some type of hash functions,
yes.
And for communicating them back to the client, you assume some underlying.
We don't assume there is a secure channel between them.
Okay.
Yeah. If you.
Okay. Thanks for the presentation. My first question is the password token deterministic?
Deterministic.
Given,
no, it is not.
So, every time it's randomized.
Yes.
And you can manage to achieve low complication when you log in.
But the PRF output is deterministic.
But
the responses are not deterministic.
So, let's say I'm a user.
Yes.
I enroll, so I set up my record with you already. And then I log in with one of the server, then I get back I get back the token. So that token is deterministic or not?
that token, it depends on the NITTG scheme that you use.
So
So if the NITTG scheme itself is deterministic, then the token is deterministic.
That
Otherwise,
means-
it is not.
that means some of your instantiation may be deterministic.
The NITTG part, yes.
Then my worry is, so now suppose you are the server. I log in, I somehow get hold of a previous successful authentication traffic. They just test it against each other. So like you are one of the server,
Yes.
I already successfully logged in once, I provide my password, and somehow the attacker get hold of that password token.
Yeah.
He keep it in mind, I log in again, and then that's deterministic, so I just can test against it. That means if I just compromise one server, I can just
Oh, you're
launch my attack.
saying if the token itself is deterministic,
Yup.
then you can use it elsewhere and so on. But
Not
most
really
of the time,
elsewhere, but your guarantee is I must compromise T server, right?
So most of the time, actually, in reality, the tokens also has a timestamp, for example,
Okay.
with it, and most of the tokens are short term.
Okay.
Like for example, you can only use the token for 2 hours or 1 day and so on. And then if you want to use the same token tomorrow, it will be a different one.
Not really about reusing, but
Even if
anyway.
you have the
So
partial token, and you cannot reuse it most.
okay, so I see maybe so given different timestamp, the token will be different.
Yeah.
I see.
that-
Thank you so
of
much.
course.
Thanks for the nice talk. One thing I was wondering is that, so the sign-up process for the protocol seems kind of similar to the sign-in. So I was just wondering if gives the attacker any advantage if it's fakes. So it seems like it's doing a sign-in, but actually it's a sign-up. Does it help with the attacker at all?
Yeah, the sign-up phase is very similar to the sign-in phase, but the attacker has to use a different username if he does the sign-up.
Oh, because you will check the username.
Yeah, we will
first.
check if the username already exists.
Oh, I see. So another question is about does your protocol support efficient refreshment of the keys? Like, for example, maybe not all of the T servers can be simultaneously corrupt, but if an attacker can corrupt one of them at one time and then later corrupt another one, and if
We didn't.
over time it can corrupt all T of them, then
I think we only consider up to T-1 corruptions. If over time you're corrupting more than T-1, there might be an issue.
yeah, I just wonder if you can, for example, change the key for just not having to do the setup again.
Yeah, you can change the NITTG key. Actually, that's independent from the TOPRF key.
And that setup is cheap or
Yeah, that's just a one-time setup. If you want to change the key, you can change the key anytime.